All right, very good. Now we're going. Now we're recording. All right, so we're going to continue on with chapter 22. We probably won't finish all of it today, but don't ever worry about that in terms of finishing chapters. I've always built a little bit of what I call fudge factor into my schedule so that if we run long in a chapter or two, it doesn't mess everything up. So don't have any anxiety about any of that kind of stuff. I've got that all under control and taken care of. You just sit back and enjoy the ride. I'll make sure that we get to where we need to go. So here we are in chapter 22 talking about Darwin and this whole idea of evolution. Now, interestingly enough, you're going to learn today that in Darwin's book, in the Origin of Species book that we all, where he put together this theory of evolution by natural selection, he never even really used the word evolution. He never used the word evolution at all. He used a phrase called descent with modification. And that's basically the same thing. But remember, it helps maybe to think of it more descent with modification, because you recall evolution is when a population's genome, its genetic makeup, changes. And we discussed a couple of, more than once in class, how that's not necessarily good, and that's not necessarily adaptation. So if a bunch of, remember in class I gave you the example, a bunch of folks from another part of the world came into our population, the genetic information would change, but it not necessarily more adaptive or less adaptive. In some cases, like with the cheetah population, the genetic information changed. It actually got less variable, and that was the opposite of adaptive. That was maladaptive. But that's still evolution, you see. The trick that Darwin had with the whole theory was evolution. He came up with the correct mechanism, and the mechanism that they was trying to explain, what the mechanism was trying to explain, was adaptation. Organisms becoming uniquely efficient in their environment, becoming very good at doing what they're doing. They don't have to be perfect, remember, right? All they have to be is a very good at that place and time in extracting the resources they need to survive and thrive. Okay, thrive in terms of producing offspring. All right, so remember we went the other day through this whole thing about not knowing what we don't know. And if you're kind of wondering where I was getting with that, it's because I wanted you to understand. I took a class in college one time. It was really sort of a neat class. It was called The History of Science. And we talked about how the progress of science and the progress of society and, societal values and thoughts and morals along the way, how that influences science and science influences society, right? And the reason I really love the class, so the reason why I go back to Aristotle a little bit is I want you to understand that Aristotle, bright guy, was a brilliant individual, but he laid this framework that Darwin, when he came onto the scene about evolution, that he had to overcome, because for thousands of years we thought the way Aristotle laid it out, things were made on a ladder and there was nothing in between the rungs of the ladder, so species can't change one into another, which is completely different from what we talk about with Darwin's theory of evolution, right? That's exactly what we're going to be talking about, is species changing one into another. Species, groups of organisms, fish becoming reptiles. But according to the scale of nature that Aristotle put together, that can't happen, right? And according to natural theology, this whole idea that complex design must have a designer. So that what we're doing with natural theology is basically the same thing that Aristotle was talking about, was classifying critters and putting them on this ladder of life. A ladder is the opportune word there, isn't it? Because a ladder only has set rungs. There's no space between the rungs of a ladder. Species can't fall in between, okay? So, this is the thought process, and not only amongst, the theologians and Aristotle way back then, but even up into the 18th century with a guy named Carlos Linnaeus that I introduced you to. He was the fella who had the kingdom phylum class, right? He was the taxonomy guy. That's what he did. Now, he was a scientist, okay? But even Carlos Linnaeus at this time, down below, was saying that organisms being placed into class Mammalia, phylum Chordata, all right? Any of these words that we're going to become very familiar with as the semester goes on, Just because you were in a particular phylum or an order or genus, it doesn't mean, according to Carlos Linnaeus, that you were necessarily related. It's not kinship, according to him. It was just how you were created. All right, so again, that's the Aristotelian influence, the rungs of the ladder, the natural theologian influence, you know, the ladder of life, the God's created steps, the classification, nothing in between. Now, I don't know much about Linnaeus. He was a brilliant scientist, a brilliant man, but I don't know much about him as a human being. One of the things, if I was going to explain, well, why was Linnaeus? Why didn't he accept the kinship thing? Well, you remember at this time, the prevailing thought about Earth is the Earth is relatively young, right? About 6,000 years. And geologists, although we talked about this the other day, geologists were demonstrating that that wasn't right. They were demonstrating that the world's a lot older than 6,000 years. That wasn't out into the public yet. You see, the way it works in science, when you do some scientific work, you collect the data and you analyze it, you write up a paper, and you hope to get that published in what we call a peer-reviewed article, or a peer-reviewed journal, excuse me. So it's a peer-reviewed article in a peer-reviewed journal. Scientists love nothing more than poking holes in each other's ideas and theories. Now, that doesn't mean that they're cold-hearted, pragmatic individuals. There are some that are kind of that way. But that's absolutely crucial to good science. You have to have that type of mentality. You have to be able to deal with that kind of criticism. You have to be able to dish out that kind of criticism against your peers so that we're always make sure that we're eliminating, and this is kind of going back to Plato again, eliminating the bias. We're trying to make sure that we get the right answer, as close to the truth, quote unquote, as you possibly can. Now notice in science we kind of split hairs a little bit with terms. You learned in Bio 1 about theories and hypotheses, and perhaps you learned that the hypotheses are never proven, they're never disproven, they're supported or they're refuted. You see the difference between the two? One is more definite. It's proven. It's not proven. Whereas in science, we always leave the door open. All the evidence we have supports the theory that the Earth spins on its axis, causing day and night. Okay? And that's where statistics come in. The chance of that happening has a very high probability. So if you're standing out on a beach at night, looking up at a bright light as the sun's going down, you might generate more than one hypothesis as to what is that? A star, a planet, landing lights on an incoming aircraft, yeah, or a UFO. Now, one of those, has the least probability of the others, right? And that's what we do in science. We never say it's definitely not a UFO, unless, of course, the thing flies over. Now we know it's a plane. But if we never see what that light actually becomes, then we don't know for a fact it's definitely not a UFO. You can't prove that UFOs don't exist. All right? Nobody's proven to me, anyway, sufficiently that they do. I remember as a kid, there were always these pictures of UFOs, and it was always this black and white, grainy, out-of-focus thing that looked very much like a Frisbee. What I find funny is in today's age where everybody's got a camera on their phones, right? I mean, for one thing, folks are born with phones attached to them now, and yet nobody has gotten, these cameras are all, bazillion megapixels? Nobody's gotten a good shot of a UFO. Even though there were all kinds of photos back then when I was a kid. Does that mean there isn't any UFOs? I don't know. But nobody's showed me anything yet to make me prove that. But that's what we mean about science. So when Carlos Linnaeus was putting this taxonomy together, maybe the young Earth is kind of what threw him off. He's like, wait a minute, these things couldn't have happened, because of the fact that the Earth isn't old enough. It's only 6,000 or so years, right? Which, of course, we know is different today. Now, I don't want you to get sweat about this slide too much. This is really just a sort of a summary of the people I'm going to go through, kind of that history of, it's kind of the evolution of evolution, basically. We are going to talk about all these people and have been talking about all these people. I think it's good to kind of put it on a timeline, on a scale. Remember, Darwin didn't invent this whole theory of evolution, right? It was around even back with Lamarck that we talked about in the early part of the 19th century. The mechanism of evolution was really kind of the trick, all right? And whether what we were seeing as changes in the fossil record were really happening, like when we discussed Lamarck stuff toward the end of class on Tuesday when we were together. All right, so let's go to the geologist and just review once again, what is it that Hutton was saying? How is this important for Darwin's idea? Well, Hutton was saying that basically, if we accept the fact, yeah, no kidding. If we accept the fact that water can erode rock, now is that a fact? Can water erode or break down rock? If I told you to take a bucket today, a Home Depot bucket load, I don't care, I'm not trying. Anyway, put water in it and drop a rock in there. Would that rock eventually erode? Would it dissolve, which is not the right word, but you understand what I'm saying? Would that happen? Yeah. By tomorrow? How long would it take? Yeah. Centuries, years, a long time. So how long do you think it would take for that river, water? Now, admittedly, when water erodes rock, the water becomes very heavy and silt, right? So water, in this case, you can actually see that the river is a kind of brownish color. That's because of all the sediment that's in it. The river kind of becomes a liquid sandpaper in a way, but okay, it's still water. So how long do you think it would take for water flowing over a landscape, just like you might see water flowing back along the beach as the tide recedes, to cut down through solid rock to the depth, in some places the Grand Canyon's a mile deep? Is that going to take you a long time? Yeah. Heck yeah, it's going to take billions of years. A lot longer than 6,000 years, right? And what Hutton was saying with his idea of gradualism is these changes that we see. Sure, absolutely. There's lots of things. It's going to be like sandstone versus granite. How much sediment is in the water? How steep the gradient is. You know how right, the hill of the water. Water flows faster in a steeper hill. All of that's going to affect it. But what Hutton was saying is kind of what I told you guys about the field notebook and an elephant. If we were eating an elephant, you could do it one bite at a time. Yes, water can erode rock all the way down to the depth of a mile, given enough time. Okay, so the world's probably, we're definitely refuting the idea that the world is 6,000 years old, because there's no way, geologists will tell you, it's laws of physics, folks, and the laws of physics don't change. We orbit around the sun, right? And if they discover, which they did, oh yeah, that's right, in the news last night, did you hear the story about the planet they discovered that's an Earth-like planet at the star that's nearest ours, which I think is Alpha Centauri, is supposed to be the star nearest ours. But there's an Earth-like planet out there, which means there may be water on it, there may be living things. Oh my God, that's just incredible to me. To think that in my lifetime we might actually find fairly irrefutable evidence that life exists on other planets it just makes my head swim. I just find that incredible. Considering when I went to school, we only learned about 9. Now there's 8, 9 planets, and now there's thousands of other planets out there. Okay, but if we observe this other Earth-like planet, right? I'm trying to get my hands in front of it. There we go. That's right. There's all, and that means that some of them have planets, and if you do the oh, yeah. See, that's the hard part. That's a good point, George. That's really the hard part of all this, is the fact that it's universe, yeah, is the fact that we may never know. Unless we learn some way to travel space-time, going to a planet that's millions of miles away, unless they send us a radio signal, unless they're intelligent life. Now, if it's just bacterial life, they're not going to be sending us any signal like that. But, what I was trying to relate to the gradualism about is the fact that, we can assume that planet, that new one we're just talking about, orbits its star, its sun, the same way ours does. Because it's physics, right? If you've taken physics classes, it's angular momentum and blah, 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 and elliptical orbits and all that sort of stuff, right? So the laws of physics govern how fast water with a particular sediment load would erode the rock. And it's going to take longer than 6,000 years to make the Grand Canyon. Okay? All right? Gradual change. All right. Now, jump into sociology. We were talking a little bit about sociology right before class. Remember what Malthus did for this whole theory of evolution. He really didn't do anything directly. What he did is he influenced Charles Darwin. Darwin, when he came back from that round-the-world cruise, that 5-year thing that you learned about in Bio 1, he was convinced that organisms had changed through time. He was convinced that what Lamarck had seen in that stratum of rock was real. He was convinced that it wasn't a ladder like Aristotle, but it was the mechanism he didn't know yet. Remember, Lamarck had gave us a mechanism already. We've only discussed Lamarck's mechanism for evolution. That was the stretching of the giraffe neck. I'll go through that in just a minute. But let me stick with Malthus, because here's Malthus's spark to Charles Darwin. Malthus basically said among human populations, as time goes on, the amount of resources increases, right? We go from hunter-gatherer to agriculture to better at growing crops, right? That kind of stuff. But that the population of humans grows faster. So it's an exponential growth. And Malthus, being a sociologist, was talking about back down here, there's not a lot of problem. Most everybody is getting enough. But he suggested that when we get to these kinds of situations among humans, that there's going to be all this strife and civil war and pestilence, and it's just going to be a horrible place because there's going to be a lot more people than there are food. Yep, and we can do that. It's an interesting point, Bradley. Yeah, we can do that. We don't have to see a living thing. If, for example, we can analyze the light coming off of a distant planet, and in that light, we can see whether that light indicates the presence of chlorophyll. Okay, I'll let that bounce around for just a second. Chlorophyll. So if we found a planet that had chlorophyll in it, or on it, or in the planet, or something on the planet had it, what would that be telling us? What's going on that planet? What specific thing that you learned about in Bio 1? That's right. There are photosynthesizers up there, aren't there? Yes, that's exactly right. Textbooks and then money down below. Which is there's a big shift going on in colleges now, folks, and that is the idea that we're going to be going with textbooks that aren't that are going to be free eventually. Which will be nice for you guys, because I sympathize with you. That's right. So we got some photosynthesis, and photosynthesis can only happen in living things. We could detect the presence of respiration by looking for waste gases, carbon dioxide, which occurs in many other ways, not just respiration, but we don't have to be on the planet to see that. Anyway, when this gap gets really big, okay, I'm not sure if Malthus ever said this in his book, but this is what Darwin took away from it. He said there's going to be a struggle for existence. There's no struggle down here. Everybody's cool. Maybe some are struggling there, but way up here, there's going to be a massive struggle for existence. And when there's a struggle for existence, there's a winner and there's a loser, right? And there's everything in between. So that if you think about what Darwin was thinking about in the struggle for existence, he means that if of a particular species, there's only X amount of resources, but there's, X plus some value of population, then that means that there's going to be these winners and losers. Now, I want to change that word right now so we understand. I've used the word winners and losers to begin with because I think that's where most of you see. Yeah, unfortunately. That's right. Absolutely. That's another thing that he was talking about. But instead of winners and losers, let's use terminology more appropriate when talking about evolution. Let's call them more fit and less fit. Fit has to do with your reproductive fitness, okay? How many offspring you leave behind. So we're gonna come back to that. Mutations can increase or decrease fitness, Bradley. Yes, absolutely. Mutations very often decrease fitness. Usually, usually they decrease fitness, but mutations can also increase fitness. Mutations are random. So sometimes when you roll the dice, you get a good number. You mean genetic variation? Is that what you're talking about? Yes, that's part of it. But in terms of sexually reproducing organisms like you and I, okay, the major form of genetic variation occurs during prophase 1 in meiosis. What occurs during prophase 1 in meiosis that lends to genetic variability? What is that process called? It hasn't been that long since y'all had Bio 1. You remember meiosis had a very different result than mitosis. It was trying to create cells that were genetically non-identical. Yes, the DNA was copied. You're right, Tiffany. Come on now, but what else? It happens in prophase 1. We talked about homologous chromosomes, and they do something. What do they do? Come on, folks. They do split, but they do in mitosis too. But before they split in prophase, the homologous chromosomes, remember the homologous? Oh, perfect. Nice. Crossing over. Thank you, Sky. Crossing over. That's what they do. Now, you remember what crossing over does? Yeah, you got those tetrads, and they're crossing over, but yes, that's what it does, Tiffany. Yes, it shuffles up genetic information. And every time those homologous chromosomes get together, make an egg or a sperm, they cross over in a different spot. I think it's typically homologous chromosomes cross over in 1 to 3 spots every time they make a gamete, but they do that in a different spot. And then in metaphase 1, they can line up differently. Remember, that's all that variability. Okay, now, back to the idea of mutations. Mutations can cause variability, but most times they're bad. The organisms that benefit most from mutation as a source of genetic variability are things like prokaryotes, the bacteria, the archaea. Now, do they suffer from bad mutations more than good? Yes. How do they get around that, though? How do bacteria use mutations to their advantage, even though I'm telling you, most of the time mutations are what we call deleterious. They're bad. What does it bacteria do, prokaryotes do, very different than the rest of us eukaryotic critters, most of us anyway, that allows them to deal with the fact that you're usually going to roll bad dice, because that's what mutations are. They're random. They're like rolling the dice. Come on, you guys are on a roll. The bird with the long and the constant with the long beaks to get at those. Yeah, but not once. Something like that would occur through generations and generations of that kind of stuff. Yeah. All right, folks. So what I'm saying though, what is it about prokaryotes that will allow them to still survive today? There's more of them than there are all of us. Even biomass, if we weighed up all the prokaryotes, they weigh more than all of the eukaryotes combined, folks, all the animals and the plants. What is it about bacteria that allow them to use mutation as a really good source of genetic variation, when for the rest of us, you might get a good one, but chances are you get a bad one? How many offspring do you produce average in a lifetime? How many? Yeah, they mutate. Viruses actually can help them with that. Okay, you're close there, Tiffany. The reproduction is the important part. What's the reproductive rate of an average E. coli prokaryotic cell versus, say, a human being? Yeah, there you go. You got fission. How many offspring does an average prokaryotic cell make in its lifetime versus, say, you? Yeah, right? So look at this. If we say that 1 out of 1 billion mutations is a good one, 1 out of 1 billion, 999 million, blah, 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 are bad. 1 out of 1 billion. E. coli can produce billions of cells in a very short period of time. So the way bacteria can use mutation for variability versus where it's a little bit more difficult for us is reproductive rate. Remember what I told you about the sea turtles? They lay, 100 eggs in a nest? On average, about 1 egg out of 1,000. Now, when we say it's successful, what I mean by that is that egg hatches and that organism lives to reproduce itself. That's a successful offspring, because that genetic information, if you die before you reproduce, dies with you. So bacteria can get away with using this. My mother used to say when I was getting close to being in trouble as a kid, poking the devil with a short stick. Bacteria can do that. They can play with this mutation thing. And again, when you start monkeying with DNA, DNA is pretty special. You got a pretty good chance you're going to screw it up. But if you reproduce a bunch, you can play the odds. Yes, absolutely. Oh boy, very good point. Absolutely. And because they can reproduce so rapidly and take advantage of... Now, every time your DNA makes a copy, like during replication that you learned about in Bio 1, it's not perfect. Now, there are things that go along that try to make it perfect, and you don't want mutation, but if you do enough copying, mutations are going to be introduced. And so what Bradley's pointing out, that's right. You can get away with that, with dealing with these, mostly having a chance of getting a bad mutation if you make a lot of offspring, which means you can reproduce very quickly and evolve very rapidly. And that's the problem that hospitals have been having with antibiotics. Antibiotics, when you treat bacteria with an antibiotic, what you're basically doing is you're selecting for those who just through random whatever have the right genetic information to basically thumb their nose at the antibiotic. And then when the antibiotic kills everybody else, they're the ones that reproduce, right? All right. Excellent. Very good. Good discussion. All right, let's go. Well, next one. Lamarck, all right, he saw the lines of descent. We won't. Well, see, now smallpox is in the Center for Disease Control. From the last I know, there's only... the only place smallpox is found is in quarantine areas in like the Center for Disease Control. But wasn't that smallpox that they found in that box somewhere? There's some story from a couple years ago. I can't remember what it was. And occasionally we do see smallpox because smallpox, these things can mutate from one into the other. That's like HIV. That used to be a simian immunodeficient virus, a virus that affected monkeys and mutated into one for us. Yeah. Oh, yeah, maybe you're right. Trying to remember. Yeah. That's why we have to be careful with that kind of stuff. Years ago when a mother would bring her child to the doctor with had a cold, the doctor would, very liberally would prescribe antibiotics. And now they're not quite as much anymore. Right, exactly. And that's a very good point, Kelly, to bring up. Not vaccinating your children, unfortunately, what that does is it puts other children at risk because people think just because my child's vaccinated against something, that it means there's no way he can get it. Well, no, that's not true. That just lessens your chances of getting it. So if a child who hasn't been vaccinated brings it to school and spreads it to your child who has been vaccinated, there's no guarantee they won't get that disease. Yeah, that's right. That's right, absolutely. Okay, so and I hate to be on a political stump here because it's not really political, but I think about some of the people that support not vaccinating their children, and the one woman on TV was saying that she got her information off Google. That's how she knew it was right. I'm like, oh please. Yeah, that's right. That's where thank you, Sky. That's where smallpox came from. It was a mutated cowpox. All right. All right. This is awesome. All right, here we go. So Lamarck's saying that we look through a layer of rock, and as we go up or shallower in the layer of rock, we're coming more present in time. I said that totally backwards. Not backwards, but convoluted. This rock layer is older than this rock layer, right? It's the way sediment lays down. Again, that's common sense. Nobody would say, well, like the yellow layer was last and the brown layer came before that. It makes perfect sense. And Lamarck was looking at critters and said, wow, the ones in the older strata, died and are extinct and not around anymore. The ones in the newer strata are either around or more recent, and they kind of look like they might be similar. And if they look like they might be similar, then that means they might be related. They may have evolved from one into the other. Now, and that's very true. That's a very reasonable observation, but unfortunately, when we get into this idea of what constitutes a species, which is in the next chapter, perhaps the one after, I don't recall exactly, you're going to find out that just because something looks the way it does, doesn't mean it's very closely related. You're saying, let me give you a good example. Shark and a dolphin. Now, I know everything at some point is related, but we're talking close relatives. Sharks and dolphins are very different animals, aren't they? They're different groups of animals, aren't they? But they look an awful lot alike. An awful lot alike. And if you're wondering why that is, you remember one of the biggest things that Lamarck actually gave to us, or one of his major contributions that he reinforced in the idea of evolution, was that organisms are going to evolve. Now, he had the mechanism wrong. Okay, this whole thing of the stretching of the neck, he had the mechanism wrong, but the fact that the environment is what's causing these critters to have to adapt. Remember, you don't have to adapt. You can go extinct. But if you want to survive, you must adapt. And it's the environment that's causing that to do that. If the environment doesn't change, if it ain't broke, don't fix it. If the earth doesn't change, critters don't need to adapt, right? Common sense. So even though Lamarck had the mechanism wrong, his mechanism, we call it I'm typing this out, inheritance of acquired, the inheritance of acquired characteristics. Evolution is the change. Lamarck saw change, right? He looked at the fossil record, and he said the mechanism was the inheritance of acquired characteristics. The ancestor of the okapi and the giraffe, the stretching of the neck, I'm trying to do this in the camera. The stretching of the neck is an acquired characteristic. Me shooting free throws is an acquired characteristic. Lamarck believes somehow that could affect your sex cells, affect your offspring, and they'd be born with longer necks, or they could play basketball. Okay? Not a bad start. Remember, science is all about alternative hypotheses. All that's very reasonable, except for the fact of there's no way what occurs to me in my life today, my stretching of my neck, my shooting of basketball, could ever affect the sex cells, right? So, right idea, wrong mechanism. Boy, good question, Kelly. It was a little of both. Most living things I love this class already. We may need to take 2 semesters to finish all this. But anyway, most organisms in the ocean live near land. There's not a lot of what we call productivity out in the middle of the ocean. So most critters live near land, near shore. So if you think about it, there's a lot of critters crammed into relatively small areas. So yeah, when land became available and became supportive, then organisms could have moved out on the water and land to escape over competition. But now the thing is, about land being supportive, critters couldn't move out onto land until there was something to eat. So the first organisms to move onto land had to have been the producers, right? The plants. So they would have been the first ones, and then the animals could have followed. So once the food, if you will, started growing, then there would have been kind of 2 factors: the over competition in the water, the organisms trying to avoid that, and the availability of resources on land. I mean, before there was plants on land, then there was really nowhere to go. Because unless you could photosynthesize, crawling out onto a bare rock of land isn't going to do you much good. Click on that link that Bradley sent. That's a good one. Yeah, that's further on down the semester, but we will talk about that. Yeah, the grass. There you go. Very good. Yep, got to have the grass. So good question. Yeah, absolutely. So it's a little bit of both. Okay. All right. Let's jump back to a little bit of geology for just a second, because now, again, we're kind of doing this chronologically. But at about this time, we're talking the late 18th century, yeah, the early 19th century. It's a fellow named Georges Cuvier. Cuvier was what we call the father of paleontology. We use that word a lot, father. We call Darwin the father of modern evolution, Mendel kind of the father of genetics. It doesn't mean these folks invented it. Evolution was talked and discussed, as we've seen before Darwin. Cuvier and folks were digging into rocks and looking at organisms in the rocks. That's what paleontology is, a unique mixture of geology and biology. Folks were doing that before Cuvier came along. But these were like the first big names, I guess, if you want to think of it that way. But Cuvier was not a supporter of evolution, right? Isn't that funny? I mean, just like Lamarck, he was digging through these rock layers. He made smart guy, made all the same observations more or less than Lamarck did, but instead of thinking that they descended from one another, he came up with another idea. Now, there's nothing wrong with that. Again, that's what we have to do in science. Cuvier said, I've got an alternative hypothesis, which he called catastrophism. Catastrophism, if you really want to impress your friends this weekend, give them the anti-uniformitarianism thing. There's a lot of syllables in there. Sounds really cool, but uniformitarianism is, and we'll actually see that in the next slide, but it's kind of what Hutton was talking about. Hutton's gradualism, the river cutting through the Grand Canyon, how that would, you could carve a canyon that deep with water and with given enough period of time. Uniformitarianism basically says that the rate at which that occurs, the rate at which water can erode through rock, the rate at which mountains are built up on Earth, the rate at which all these geological changes that go on Earth, the rate at which that happens has been the same since the beginning. So in other words, erosion didn't happen faster in the past. Mountains weren't built up faster in the past. All of those events that occur today occur at the same rate. So you can't say, well, maybe the world is very young because when that river that was carving that canyon was doing that, the laws of physics were different and erosion worked at a faster rate. No, that can't happen that way. But Cuvier's theory was the opposite, anti-uniformitarianism. And here is what he says. Now, in the italics as well as in the blues, little flowchart, it's kind of the same thing. So here's what he says. A catastrophic Earth event. Okay, now the nice thing about science when we're looking at some of these thought processes, everything along the way needs to make sense. Have there been catastrophic Earth events? Oh, yeah. Ask the dinosaurs. Right? They were doing fine until 65 million years ago when a rock the size of Manhattan plowed into them. That's how big that asteroid was. Asteroid astronomers, I don't know what they're called, anyway, they have sort of a macabre way of referring to the size of asteroids. They call them, like, for example, the one that took out the dinosaurs, they say that's a planet killer, and then a smaller asteroid may be a country killer, or a city killer, or a village killer, something like that. So it's sort of a macabre way of looking, but that is exactly what that asteroid did. It basically wiped out all life on the planet, for the most part, not all life, but for the most part, all life on the planet. So and we can count somewhere around six catastrophic Earth events, planet killer asteroids, basically, and there'll be other ones in the future, right? Earthquakes, any of that kind of stuff. Floods, volcanic eruptions, any of that sort of catastrophic event could cause mass extinctions. Again, that's not outside the realm of possibility. Mount St. Helens in Washington State blew up in May of 1980. May of 1980 it exploded. And if you look at the pictures soon after the dust and everything settled, it looked like a wasteland. The plants, the animals, everything was killed, dead, or gone. That's definitely a mass extinction. And then according to what Cuvier, what happened after that was then foreign species from around the area of the mass extinction, they moved into that area in which this catastrophic earth event happened. So let's imagine like a volcanic eruption. Now, does that happen? Well, yes, absolutely that happens. It happens all the time. I remember as a kid watching this old, I think it was even one of those film strip things from ancient years ago about this island, an underwater volcano erupting near Iceland, and it kept erupting and dumping stuff out of the volcano until eventually it came above the layer of the ocean. I'm getting ready to use the real pen to draw on the screen. And so here's the water, and that volcano erupted and erupted until it finally came above the ocean, actually made an island, and within a year or two, there were plants on that island. And this was, hundreds of miles out to sea. So again, all three of these, yeah, check, that happens. Yes, check, that happens. Yes, that happens. So all of that makes sense. There's no, magic in there whatsoever. So of course, these foreign species coming in, to us when we observe it, looks like the local species composition has changed, and it has. But he says not because it's evolved there, Lamarck. Not because it's evolved, but simply because the species that were there that you looked in the fossil record died, they went extinct, and then the new ones that looked like them on top came from surrounding areas. Okay, now that does happen. All right, so Cuvier's not totally wrong. That does happen. All of those things he talked about. No, the Marianas Trench is caused by two tectonic plates in the Pacific mashing against each other, and oftentimes what happens, one plate will go over top of the other one, but in this case they both dive down from a trench. 35,000 feet deep. I always tell my my marine science students, think about being on the surface of the water, looking down to the bottom of the Challenger Deep, and that's the same distance as when you're flying at cruising altitude in most aircraft. So next time you're in a plane flying at cruising altitude, look down out the window, think about how small the ground looks, and that's the distance to the bottom of the Mariana Trench from the surface of the water. Okay, so Cuvier, right? Yes. Right about the way life on Earth, the diversity of life? No. This happens in local little events, but it's not evolution. It's just simply organisms migrating and moving in. Okay, so it's not evolution when it happens the way he was describing. It does not explain, though, the diversity of life on the planet. It does not explain evolution by natural selection that Darwin was talking about. Okay? Make sense? I understand, and again, I haven't read Cuvier's biography, but I understand he was quite quite proud of himself, quite enamored with himself. He thought he was quite the smart guy. A lot of scientists that way, right? Okay, so here's that uniformitarianism thing, and that's what Lyell is a geologist that Darwin was most read. As a matter of fact, one of his books that he brought on that cruise that he went on, that round-the-world cruise, and this is what helped influence Darwin's idea about the old Earth and changes on the Earth, right? So, Lamarck's already kind of, and other people are already talking about the evolution being, the driving force being the environment. The environment is old, it's changing, okay? And what Lyell was saying with uniformitarianism was he took Hutton's gradualism theory and he expanded it. And he said, all right, the rate at which that river is carving through the rock, or the rate at which erosion, here's erosion, occurs, is the same rate it's always been occurring since the beginning of time, right? Okay, it wasn't faster in the past, it wasn't slower, so that means there's got to be a lot of time. Now, the reason why I have a seesaw in there is because here's where we expanded gradualism. Lyell also said the formation of land, okay, the formation of terra firma occurs at about the same rate. And that's what this picture is over on the right. It may not be the best picture, but what we got again is two slabs, two plates. Remember, the Earth is basically like a cracked egg. The crust of the Earth is like pieces of this cracked egg floating on this semi-liquid magma, this hot rock down below, this liquid rock, if you will. And so these plates crash into one another, and they make trenches, where they dive down really deep, like we were talking about with the Challenger Deep. In other ways, as I mentioned, one slab climbs over the top of another one. And eventually, if this continues, that slab will come up out of the water, right? Yes, GRBs, gamma ray bursts. That's right. Yep. Gamma ray bursts come out of neutron stars, rotating neutron stars, and if we were in the direction of a gamma ray burst, no matter how far out in space it was, it would fry us. Now, although they happen, the point is it's a big space, a big universe out there. So, luckily, yeah, neutron stars form from that explosion when the star collapsed back in the black hole. They spin around really fast and they put out these gamma ray bursts. I think you're right. Black holes do it too. Yeah. So there's even that out there. So there could have been some extinction events from that. Let me show you a really cool picture that I found that shows this idea of one set of rocks pushing up over another one. Let me go back here. Here, there it is. Okay. This is the Matterhorn in Switzerland, and I saw this on a show last spring, I think, and it was just so fascinating. Notice how the Matterhorn is shaped, right? It's got this face over here. If I was going to make it looks like a triangle that's been pushed over, maybe like a dorsal fin kind of thing, right? Or like slumped to the left. All right, now here's why that is. This is direct evidence of plates colliding with one another, and sometimes they dive, sometimes one climbs over the other, and sometimes they push against each other and basically form a wrinkle in the Earth's crust. So what this is this right here is part of the European plate. This here is part of the African plate. Now, the African plate contains more than just the continent of Africa, because we're talking about Switzerland here, and obviously that's not in Africa. The African plate includes, southern Europe, as well as it includes anything south of the Alps. That's where the Matterhorn is. So, and they've done geological analysis on the rocks, and these are rocks from the plate on the left, and these are rocks from plate on the right, and these rocks are more similar to other rocks that come from Africa, and these rocks are more similar to other rocks that come from Europe. So that's exactly what you're looking at. You're looking at two plates pushing against each other, and it looks like the African plate has got a little bit of an advantage and is pushing over top of it. Isn't that neat? Yeah. It's amazing to look at that and say, that you can see it. You can see where my hand, right? You see where the plates are pushing over one another. Well, I mean, the Marianas Trench would be diving between those two plates, right? So if you got two plates that dove like that, then, when they took like the Bath Escape Trieste, when they took that deep submersible back in the 50s, that's what they did. They dove down to the bottom of the Marianas Trench. Okay, let me go back to my other one here. I always want to double click with a single click. Line. All right, so we were here, right? So what Lyell was saying is he just took Hutton's theory of gradualism and expanded it, right? He said, yes, the rate at which rivers carve through rock and the rate at which sediment, right, land ends up in the ocean is at the same rate it's always been, and the rate at which ocean land is made into ocean land, the way the bottom of the ocean rises up to become land occurs at the same rate. Very slow, right? Very gradual, very slow, but nonetheless at the same rate. Not faster in the past, not slower. It's all at the same rate. So once again, more evidence that supports the idea that the Earth is a lot older than 6,000 years, right? Earth's got to be a lot older than 6,000 years. All right. Any questions on that? So here we are, with Charles Darwin. And remember now, he was a very well-read on geology, so he's got all these ideas in his head. He's heard about catastrophism and gradualism, and he's very learned about all that. And he's traveling all over the world, going on this round cruise. And there's a couple of things, many things that he noticed, but there's a couple of things I want to point out. For one thing, when he climbs to the top of the Andes Mountains, which are on the west coast of South America, near Chile, or in Chile, he finds at a very high, something like 10,000 feet, if I remember correctly, he finds fossils of marine organisms. Now, how did those get there? How did those marine, ocean organisms end up in a situation where they become fossilized and then found 10, 15,000 feet up a mountain range? Yeah, that's exactly right? So we have two plates coming together again, and we got organisms. They die, they become fossilized, those two plates push up, Darwin hikes along, here we go, and you can find them at the top of a mountain. Once again, showing you that the world is very different now than it was back then, that what used to be the bottom of the ocean is now the top of a mountain. Once again, showing that that's a long period of time for that to happen. Okay? So he's building his cases, he's building his evidence. This idea of these marine organism fossils comes about because the rocks were uplifted. And these are areas that coincide with areas of lots of earthquake activity. And earthquake activity is direct evidence, a direct result of these plates crashing into one another. Because sometimes when the plates crash into one another, they stick. Like in California, the San Andreas fault, the plate on the west side is moving north. The plate on the right side is moving north, but slower. So these plates stick, and every once in a while, they break loose, and that's an earthquake. Okay? World is changing. Mountains are forming. Canyons, trenches are forming. Okay? World is different. Now, he goes to the Galapagos Islands, which are just off the west coast of South America. The Galapagos Islands are what we call an archipelago, and I think we talked about archipelago. We talked about this in class. An archipelago, like the Hawaiian Islands, is a group of islands relatively close to one another. Oftentimes, if we're referring to an archipelago, we're going to be saying islands, like the Hawaiian Islands or the Galapagos Islands. There's not a Galapagos Island. Philippine Islands, very good. Yeah, excellent. Beautiful place. That's right. Actually got certified as a scuba diver in the Philippines. All right, so this Galapagos Islands is an archipelago, and we'll talk a lot more about Darwin and the Galapagos Islands and what he saw there. But I want to introduce you to it. Some of you may have heard about Darwin's finches. A finch is a bird, and Darwin. It's not that Darwin owned them, but here's the thing: when Darwin went to this Galapagos Islands archipelago, he found that there were a dozen or more species of birds that were very similar to one another, but nonetheless, they were different species. Okay? They were all finches. As a matter of fact, and it varies from where you look, he cataloged somewhere in the vicinity of 13 species. You see in the picture down below, they've got 14. I've actually seen some results that they're more like 15 species. It kind of depends on how you split these birds up. But there were, woodpecker finches. Look at that, using a tool. Is that neat? Whenever animals use tools, biologists' behaviors just come unglued. Because that's just, he's probably sticking that little stick in there to get grubs or insects to attach to it. Yeah, that's right, like the Hercules Club. Sure, for its cash, and then when he pulls it out, there's insects on the end of it. Maybe you guys have seen the pictures. Years ago, they took tried to figure out cognitive learning. Cognition is the ability to solve a novel problem, something you've never seen before. So they put a monkey in a room, and they tie a bunch of bananas up, in the room, like maybe 10 feet above the ground, right? High enough that the monkey can't get to it. And there's nothing else in the room but a bunch of wooden boxes, several wooden boxes. Does not take the monkey too long to figure out if I stack the boxes on top of one another, I can get to the bananas. And behavior is just like, wow, that's so cool. Because, again, it's using tools, or like the otters who have the rocks that they use to bust open the sea urchins and the mollusks that they feed upon. Tool use by animals is Yeah, that's right. Because it's all very, very put together. Learned versus inherited versus, yeah. See, uh, generally, inherited behaviors are those instinctual ones. And then learned behaviors can occur through two types of conditioning, what we call classical conditioning and operant conditioning. Classical conditioning is what Pavlov did with the dog. Ringing the bell, okay? The dog heard the bell, he started salivating. That's classical conditioning. The doorbell rings, Cooper goes crazy, my dog. That's classical conditioning. Operant conditioning is the animal learning when I do something, here's what happens. Operant conditioning is what a kid learns when he's touching a hot stove. Ow! Don't do that again. You can use the computer. Yeah, exactly. Yeah, exactly. Same idea. But it's all a higher thought process, right? But anyway, we're talking about finches too. So different species of finches. Here's what Darwin suggested. Here's his hypothesis. He suggested that the distance from South America to the Galapagos Islands was a pretty good distance over water, and that most of the time, typically, a finch saying, heck with this, I'm heading on over to the Galapagos, would not make it. Fall into the water, drown, blah, blah, blah. It's over, right? Never hear about it. But maybe some finch or a finch could have been a single fertilized female carrying an egg, could have been just one, by luck made it across. Maybe there was a windstorm. It's kind of the same idea that we think how egrets maybe got from Africa to South America and then made their way up to where we are. Maybe they were blown over the Atlantic Ocean, which is a good distance, by a windstorm. And, it's hurricane season. That's how the storms move, east to west. So that's very possible. So the same thing with the finches. So Darwin thinks that suggests that maybe could be, again, a single finch or a few of a particular species from the mainland flew over to one of these islands. And the nice thing about the Galapagos Islands, it provided a really great living laboratory because each one of these islands are slightly different in different habitats. So there were slightly different environments in each one of these islands. And not only that, as the birds began to reproduce, they began to compete. And when they began to compete, there was, of course, the chance that you might die because you become the least fit. But one of the things that competition would drive, wrong way, Steve, would drive diversity. Now, if I'm a woodpecker finch, or if I'm an ancestor of the woodpecker finch and say the large ground finch, and we're competing for the same resource, and one of us says, hey, I can use a stick to find these grubs, less competition, that species is going to be preserved. So Darwin's idea is something that we call adaptive radiation. It happens on archipelagos very often with organisms. They make their way out to the archipelago, and then they radiate in terms of not only to different islands, but also in species diversity, and they do that by adapting. So that's why they're really interesting living laboratories. We can see this whole idea of these organisms adapting to these slightly different environments as they move between them. All right, so there's lots of other things that Darwin had in his head, but eventually makes his way back home, and he starts to think. See what he wrote right there? I love this. Here's Darwin's notebook. I think. And he's basically drawing out a family or a species or an organismal tree or bush. The diversity of life is what he's drawing there. And you just look at that and you think, wow, this guy, just amazing. Can't really read the other notes, but I would love to see what else he's written in these things. This is 1837. He doesn't publish his book on evolution till 1859. So this is almost 22 years before that. But here's what he says. He says that extant species, extant is the opposite of extinct. All right, so critters that are around today descended. Now, he didn't use the word evolution, like I said. They descended. They arose through time from ancestral species. Okay, so this would be an ancestral, and then these would be descendant species. And some of them would have gone extinct, and some of them would still be around. They'd be extant. Okay, so he's supporting what Lamarck said. Supporting what Lamarck said, not countering or not refuting Cuvier, because Cuvier, of course, what he said, again, in small scale does fit. But what he still doesn't have is the precise mechanism. It doesn't have the mechanism, right? Mechanism that Lamarck had was that inheritance of acquired characteristics. Now, the inheritance of acquired characteristics we have shown cannot happen, right? You cannot think or engage in an activity like stretching your neck that's going to change your sex cells, that change your genetics. Now, again, to Lamarck's defense on that, remember, we didn't know nearly as much about inheritance and genetics back then than we do now. So, he may not have even understood or understood well how, genetic traits are passed on, obviously. Remember, Mendel was doing all that work. Okay, so in June of 1858, so Darwin is really struggling with this, right? Not only is he struggling with the whole idea of evolution and what is the mechanism, because he's starting to figure that out, but he understands that, science isn't always popular when it comes out with theories that make people uncomfortable, right? I remember a great quote that a physicist wrote in a book, and he says, just because the theory makes you uncomfortable doesn't make it any less true. So again, that's that history of science that I've been talking about. So Darwin wants to make sure that everything's right, that he's writing up his ideas, his theory, through evolution, through natural selection, but he's still kind of hesitant. He wants to make sure that everything's right. Yeah, especially with the fact that sometimes you could get yourself into trouble if you counter the prevailing thought. Not so much in the 19th century, but there still was some of that, if nothing else than professionally being discredited. So in June of 1858, he gets a letter from a guy named Alfred Wallace, which I mentioned to you briefly when we were looking at that timeline. Alfred Wallace lived over in the Malay archipelago in Malaysia. Alfred Wallace was actually most well known for being one of the early folks into biogeography. Now, biogeography is exactly what it says. Basically is why do organisms live where they do? It's not as simple as, why do fish live in the water and cows live on land. It's more, why do certain fish live in certain areas of the water? What is it about the environment that allows or have these organisms adapted to that environment? So it's very evolutionary, right? But he was more about describing where critters are and why they are where they're there. Okay, but he writes a letter to Charles Darwin. Now, they don't know each other, Alfred Wallace and Charles Darwin, but he hears about Darwin's work, and he says, hey, I got this idea, Chuck. And he writes it in his letter, and he describes exactly Charles Darwin's idea. His idea of natural selection as being the driving mechanism behind evolution, right? Evolution by adaptive evolution. So, when someone does that, when it's an unsolicited confirmation, right, then that gives you a little more confidence you might be right. An unsolicited confirmation is like, Alfred, you think I'm right, don't you? No, that would be a solicited. But you never heard of this guy, and he rings you up or writes you a letter. I guess no phones back there, so he didn't ring you up. But he writes you a letter and says, hey, I don't know what you think, but this is my idea. So now Chuck's feeling pretty good. He's like, all right. So, and they both, by the way, shared in this theory. It's not like Charles Darwin took it away from him. They both were involved in the presentation of this information to the Royal Society of London. I think it was the Royal Society of London. Back then, one of the things that they used to do is if you had an idea, you went in front of a bunch of scientists, a bunch of peers, and then I always wonder if it was like what I've seen of the way British government works in the House of Commons. Have you ever watched British Parliament at work in the House of Commons? I mean, they're yelling at each other, and they're standing up and shaking their fist. I mean, they're really, for British being so stoic like we normally think, they're pretty doggone animated. I wonder if the Royal Society of London was like that. They were, you're crazy and all this stuff. That would be really kind of refreshing versus sort of the stuffed shirtness of many scientists. But he, with Alfred Wallace, he goes, now the reason why we don't hear about Alfred Wallace as much is because him and Darwin had a parting of the ways when Darwin began to apply his evolutionary theory to humans. That was a little different story, right? Okay, so anyway, so Alfred Wallace supports, gives Darwin the idea that, I'm on the right path. And now Darwin's mechanism of natural selection was actually a modification of something that he was very familiar with at the time, and so are you, called artificial selection. And in this example, you can see we're taking wild mustard, and through selective breeding, right? That's what artificial selection is. We've been able to create several different food items from wild mustard: cabbage, broccoli, Brussels sprouts, kale, kohlrabi. See, by selecting just the right part. Artificial selection, though, has a selector. Natural selection doesn't have a selector. Artificial selection, the selector is you. If you were a dairy cattleman and you wanted to make sure that you had good dairy cows, you would breed your better milk cows, wouldn't you? With the idea that the reason why they give better or more milk is because they're genetically that way. Or in a very simple way, if you have an AKC dog that you want to breed with and sell these puppies as AKC, you're going to select, you're not going to just have any mongrel down the road breed with your dog. You're going to select another AKC registered dog, right? So everybody understands artificial selection. And that was around during Darwin's time, right? We artificially selected for, we domesticated wolves and turned them into dogs that way, right? It's all artificial selection. But what's going on out there in the wild? You know, who's doing the selecting out there in the wild? And that's, you know, that's natural selection, okay? Now, this is Darwin's final publication, November of 1859, On the Origin of Species by the Means of Natural Selection, or, I always love to have these long titles. Notice, by the way, Charles Darwin wasn't a PhD. Okay? Preservation of Favored Races. All right, folks. Races back then was what was used to refer to species. Okay? So preservation of favored species in the struggle for survival. And what Darwin's theory does is it explains a couple of very important observations. The unity and diversity of life. All the different organisms that exist on life today evolved from a single common ancestor. So that's what we mean by the unity and the diversity. All life on Earth shares some very common characteristics, and one of them is the fact we all have DNA. All of us do. All living things on the planet do. And supporting what Lamarck had introduced us to, that adaptation is organisms matching or becoming very effective or efficient in their environment. Okay? So what is the mechanism? The mechanism is the idea of the fittest organisms survive. It isn't anything being selected. It is that among a group of organisms, some are going to be more fit than others. Why? They were born that way. They either inherited through getting a lucky mutation, or most predominantly for sexual reproducing organisms like you and I, through crossing over that I mentioned. And as I said, he didn't really even call it evolution. He called it descent with modification. He didn't use the word evolution in the first edition of The Origin of Species. And descent with modification, like you can see in this picture, we're looking at elephant evolution. And it's listed 3 extant species of elephant, 2 Asian, or an Asian, 2 African. I don't think that's right. I think there's more like 5 species of elephants now, if I remember correctly. But through time, and it's hard for me to see, but I think this is going back to 80 million years. Is that what the plot is there? Yeah. No, sorry, 60 million years. That's right. Couldn't be 80 million years. So starting at about 60 million years, there was an ancestor that gave rise to all of the things that aren't elephants but led up to them. All of the elephants that have gone extinct. We know they've gone extinct because the line ends, like Baratherium is extinct. It went extinct somewhere in the vicinity of, what, 34 million years ago? Here's today. So that's why we only have the woolly mammoth went extinct just about 10,000 years ago, just the other day. So all organisms are related from this common ancestor, and through time, they've adapted to their environment because through time, their environment has changed. Right? That's what we mean by descent with modification. So starting at 60 million years ago, there was an elephant ancestor which gave rise to elephants and manatees, by the way. Manatees and elephants are similar. Look at the nose. Elephants have that proboscis, you know, that trunk, and manatees have that very pliable nose, and hyrax is another critter they're around. But then through time, as we descended through time, these organisms were modified. Why? Because the environment was changing, and we end up with the species that we have today. That's what we mean by descent with modification. Descent with modification is the same thing as evolution. Same thing as evolution through Darwin's natural selection. Okay, so I've run out of time. We have a few more things to talk about. We'll do that next week, so don't worry about that. Start working on your field notebooks, though. And if you have any questions, you know where I am. You can get in touch with me. So I'm going to go ahead and stop the recording now.